Assalamu alaikum. Welcome to lecture 4 of chapter 5. Fracture mechanisms in metals is continuing. As usual, we will do a quick review of lecture 3 where we finished ductile fracture. So today then we will start with cleavage, the other type of fracture mechanism. Inside that we will talk of fractography for cleavage. We will of course later on do some more fractography, but this fractography is about cleavage. And then we will talk about mechanisms of cleavage initiation. As a small big topic, we will talk of ductile to brittle transition. We have done that in the first chapter in introduction, but we will now look at it from materials mechanisms viewpoint. And then the other type of fracture mechanism, intergranular fracture, and we will see how much of that we can do today. So let us quickly see what we covered in lecture 3 last time. We were talking of the Rice and Tracy model, and there is a spherical flaw, a single flaw, and there are remote stresses sigma 1, sigma 2, sigma 3, and remote strains epsilon 1, 2. And then the equation of the Rice and Tracy model, how other researchers tried to improve this, and the Thomason model, and how is the normal stress, which is critical, defined in, right, that we go from the one flaw in the Rice and Tracy model to 2 flaws, so that there is an interaction between the flaws and there is a normal reaction sigma n between these 2 flaws, right? So later on they will coalesce and combine and become a larger flaw. Then based on this, the ductile crack growth, right? So we discussed figure 513 and figure 514, which will be coming up. In one of them, that there is a sharp crack, which is the macroscopic crack, and then there are small embedded particles, which can be impurities or second phase particles or precipitates or whatever. And when you apply the load at each embedded particle, a void initiation occurs, and then it grows and coalesces with the large crack. The large crack is blunted. And then this major diagram from the theory, that on one side you draw sigma yy, the main stress, and on the other you draw epsilon equivalent, the von Mises equivalent strain, against r, the distance from the crack tip. And of course you divide by sigma naught and you divide by j and so on to make it non-dimensional. We just inserted this slide back again to remind you of what is crack tip opening, and this diagram, that a sharp crack is blunted and opened, and delta or CTOD, right, is there. So this was just inserted to remind you of CTOD, because here then we are talking of the relationship of CTOD with the ductile crack growth, and we talk here of the tunneling effect and explain the tunneling effect here, that there are shear lips and there are deformation bands, and there is a tunneling, right, that when the crack grows, then in the middle of the material it travels much faster, and towards the end of the material there is that 45-degree transition, and the shear lips and so on are formed. High triaxiality of the stress and so on. So we were explaining majorly that the crack is actually growing along the axial line of the crack at normal, at a direction normal or perpendicular to the applied load, but locally it is going along the 45-degree line. So there is a zigzag pattern. There is a zigzag pattern. It goes up, it goes down, it goes up again. But essentially, on a global scale, it is traveling along the crack, right? So we showed you this figure also, that this is how it actually happens. So this was where we ended last time. Today we are starting the topic of the second mechanism, right? Not ductile fracture, the second mechanism of cleavage, right? Which is a type of brittle fracture. So cleavage fracture, rapid propagation of crack along a particular crystallographic plane, rapid, right? Not like a crack growth. May be brittle, right? Cleavage basically is brittle in nature, but it can be preceded by large scale plastic flow and ductile crack growth. So this is right. One thing is that cleavage can be totally brittle. There is a big fracture all through and there is a cleavage surface. But on the other hand, there was large scale plastic flow and there was ductile crack growth, and because of some sudden change in mechanism, now all this has changed to cleavage. So originally there is large scale plastic flow, which means ductile crack, and suddenly it changes into cleavage. So it could be totally brittle, or it could be preceded by that initially there is this and then it changes into cleavage. Preferred cleavage planes are those with lowest packing density. If you go back to your material science, then you can find the packing density on each plane. So those planes where the packing density is low, of course there is less material there to resist your loads. So those are planes on which deformation can happen more easily, right? Since fewer bonds must be broken and the spacing between the planes is greater, then cleavage planes are those, right, with lowest packing factor. In body-centered cubic materials, BCC materials, cleavage generally occurs on 100 planes, right? 100 planes. The fracture path is transgranular in polycrystalline materials. This is major. Transgranular. You see, intergranular means along the grain boundaries. It does not break from one grain into the other grain. But transgranular means it breaks from one grain into the other grain. So this is large, and that is in normal polycrystalline material. So we will go to the figure and show you that. Now the propagating crack changes direction each time it crosses a grain boundary. We will go to the figure and you will see, if you try to remember your grain structure, that there are crystals and they keep on growing, right? And different crystals are growing, so they become grains. And when they hit each other, then there are grain boundaries. But inside one grain, the direction in which the deformation will travel is along certain crystallographic planes, but the other grain is oriented in a different way. So when it goes to the other grain, then the direction in which the deformation will easily flow changes. So this change, right, is happening. This change is happening. So propagating crack changes direction each time it crosses a grain boundary, and the crack seeks most favorably oriented cleavage plane in each grain. We just told you that in BCC materials it is 100 and so on. The nominal orientation of cleavage crack, nominal, right, that this is happening locally, again just like we did in ductile crack growth previously, that there was a 45-degree line and another 45-degree line and another 45-degree line, but overall it is following in this direction. So locally the grain change directions in each grain is changing, but nominal overall, right, global cleavage crack is perpendicular to maximum principal stress. So this is still the same, right, that the actual fracture will grow in a direction which is perpendicular to the global stress applied. So let us see here. First we are reminding you here, this A was the ductile fracture. This B is cleavage. B is cleavage. It is going from one grain breaking into the other grain, then breaking into the other, then again breaking into the other grain. And this C is intergranular. It is not breaking from one grain to the other. This is along the grain boundary. So this we will cover later, right? We have covered this one in detail, which is the ductile one, right? The dimples and so on. And this we are doing right now. So it just cleaves through the whole surface. It just cleaves through the whole material, and it is not like a growth and so on. Cleavage is most likely when plastic flow is restricted. The material is trying to deform in the plastic region. If it is restricted, if it is stopped, then you keep on stopping, and suddenly it breaks completely through. Cleavage is generally not found in face-centered cubic metals, right? We just told you that it is more preferable in BCC, and here we are again strengthening that that it is not generally found in FCC metals. In FCC metals, there are enough slip systems for ductile behavior at all temperatures, at room temperatures or higher temperatures. There are enough slip systems so that ductile behavior is favored in FCC metals. So mostly then FCC metals will not break in cleavage pattern. At low temperatures, room temperatures and below, BCC metals fail by cleavage. There are limited number of active slip systems. When there are active slip systems, right, then the material plastic deformation is happening easily. But if there are limited number of active slip systems, then there is resistance to plastic deformation, and then suddenly this cleavage happens. In polycrystalline hexagonal closed pack, remember that 90% of the metals or more are FCC, BCC or HCP, right? So that you remember. So we have talked of FCC, which generally fail only by ductile behavior, BCC, where a lot of cleavage can happen. Now HCP, they also show cleavage fracture. Sorry for my typing, this is W, right? W. Because in HCP also there are only 3 slip systems per grain. So in BCC there are less number of slip systems than FCC. In HCP also there are only 3 slip systems where plastic deformation can easily happen. Therefore here also cleavage would be a preferable thing. Ferritic steel. Ferritic steel, it is a type of steel. Of course, mostly it is ferritic in nature, not austenitic and so on. Most technologically important and most extensively studied material subject to cleavage fracture, right? It has a BCC crystal structure and it undergoes ductile to brittle transition with decreasing temperature. So ferritic steel is most important to study cleavage fracture. Why? First, it has BCC crystal structure, and we know that BCC crystal structure has limited number of slip planes. Therefore, there is a restriction on plastic deformation. So it is already a system where cleavage will be possible. Secondly, this ferritic steel undergoes ductile to brittle transition when the temperature decreases, and that means that already with the limited number of slip systems in BCC, it was a case for cleavage, particularly now when it goes to brittle transition, right? Ductile to brittle at lower temperatures, then of course the whole thing becomes brittle, and therefore cleavage, which is basically a more brittle type of fracture, is more possible, right? So with both these, so ferritic steels are a good candidate where cleavage happens, and that is why when people study it, then they study ferritic. So I have just added something which is not basically the fracture mechanism side, but what is ferritic steel, so that you are more clear. Term usually applied to a group of stainless steels with a chromium content in the range of 12 to 18%. You know, chromium is added to steels to make it stainless, non-corrosive, and large amount of chromium, 12 to 18%. The structure consists largely of the ferrite phase. Such steels possess good ductility and are easily worked, but do not respond to any hardening or tempering process. This is huge. When I was studying the steels at a higher level of masters and PhD, then this become very big. I mean, I thought that all steels can be heat treated very easily, but I came to found that many of the ferritic steels, which are stainless steels, cannot be easily heat treated. So this was a major piece of news for me. And types of applications include automotive trim and architectural cladding and a lot of other places where stainless steels are good. So this is what is ferritic steel.